Can everybody hear me okay?
Yes.
Yep.
Great. So Howard tells me that all the slides from the presentations today will be posted online, so don't be worried about taking screenshots and trying to keep up, because what I'm about to attempt to do is cram 10 person years of work into a 20-minute talk. So I'm going to cover a lot of material, and I'm available afterwards for any questions you have. I'm going to pose things as a set of assertions. I'm going to make 20 assertions in 20 minutes. Put your seatbelts on. Here we go. A couple disclosures. So first of all, for those of you who don't know, Bigfoot Biomedical, our mission is to reduce the burden of living with diabetes for persons with who require insulin. So we have two modalities, two systems that we're building. One is the Bigfoot Loop system, which most of you are familiar with. That's the flagship that we started 4 years ago. And then a newer system that we're working on is Bigfoot Inject. And what we're really trying to do is meet people where they are. So for the majority of people who aren't on insulin pumps, we wanted to provide an opportunity to leverage some of the machine learning and algorithm technology that we had developed for Loop and still be able to help them with their world. I was actually concerned when Amy reached out and invited me to give a talk on machine learning, because I thought, I wonder if we do machine learning at Bigfoot. I had to go look it up and confirm that in fact we do machine learning, both in the way we develop the systems and how we instantiate some of the therapies like physiology individualization. So we are in fact a machine learning and data science company. Does anybody know who this guy is? So his name is Josh Wills. He's a data scientist, and he's got my favorite definition of a data scientist. A person who's better at statistics than any software engineer, and better at software engineering than any statistician. So I was able to, okay, I think I'm a data scientist, because I think that matches what I do and what many of the people at Bigfoot do. So there's some definitions of machine learning and data science from Wikipedia. This is my favorite Venn diagram intersection to explain what data science is comprised, and I think that matches well with some of the motives and skills and abilities that we have at Bigfoot, where we come from the world of hacking and disrupting and thinking differently about things. We have some, I would like to think, fairly solid foundation in statistics and math, and then we do bring a little bit of domain expertise in the problem we're trying to solve, which is diabetes. Assertion 2, diabetes is a data disease. It's not a procedural disease, it's a thinking disease, it's a data disease. There's all sorts of types of data. There's the data gathered by about the user, there's the data gathered in the clinic, and then the data that we're primarily interested in, which is data that's coming from the devices that the person might be wearing. As I discovered the hard way, and as many of you discovered the hard way, life would be really easy if glucose never varied. If your blood glucose was like this all the time, then we wouldn't even be here today. Unfortunately, it's not like that. And I will go very quickly over this next slide because Marius has already covered it, but as we know, there's many factors that contribute to variation in glucose. And why this is relevant is that, I'll get that in a second. So we've got all this variation that's taking place in the world of diabetes just through normal life and behaviors and physiology. And the way that it's traditionally used to gather information about this is to experiment on humans, to perform experiments. And this is a very, very difficult path. It's dangerous, it's expensive, the quality of the data that is produced is of low quality, and there are some parallels in the autonomous vehicle world. They're facing the same thing. If you live in Palo Alto, you've seen the Google car driving around doing this thing called shadow driving, which is experimenting with humans in a sense, or experimenting in the real world. And I love the title of this presentation, talking about these challenges of exploring very large parameter spaces. We have a 42-dimensional parameter space with all these combinations of the things that can be contributing to blood glucose. How are we going to know that we have sufficiently explored those combinations of factors that can be critical to the safety and effectiveness of an automated insulin delivery system? These are just some of the challenges that are associated with data that's collected in the real world. This is very different from industrial data collection, where the data sources are pristine and not commingled and long samples. We have all these problems. Here's an example. My wife and I were very motivated when my son was first diagnosed, and for the first 3 years, we cataloged every juice box rescue that he had. So we, this was a replicated experiment on the same individual 304 times in a row, and as you can see, they're wildly different response. So these are just some of the challenges that are faced in the world of human experimentation. This excerpt from a paper highlights some of the advantages and disadvantages of human experimentation, and you see the red blocks at the bottom. Those are the ones that we really worry about on our path to commercialization and broad-scale distribution of our system. Experimenting with humans is expensive, dangerous, time-consuming. It's very difficult to control all the variables, all those other variables that are contributing to blood glucose. It's difficult to extrapolate into the broader use conditions from a clinical setting. And why am I talking about all this variation in data? For those of you who heard me talk before, I was taught something 30 years ago in grad school by my grad school supervisor that said, Lane, the purpose of control is to transfer variability from a place where it hurts to a place where it doesn't hurt as much in order to make a human's job easier. So if you think about these other feedback control loops that you live with, you're transferring variability from something you care about, whether it's your car's speed or your home temperature. You're transferring to something you care, that variability is something you care about less. Who cares if I use a little more or less gas or air conditioning? I just want the thing I care about to be maintained at a level area. And that's exactly what we're doing with an automated insulin delivery system. We're transferring variation from blood glucose to insulin in order to make a human's job easier. So we've got this is what we call it feedback and a closed loop. We're closing that loop of the sensing, the deciding, the acting, that thereby has an effect on the blood glucose. The reason why it's important to have some understanding of this variability is you can't transfer variability if you don't know its character. These are just some examples of the sources of variation that are entering closed loop systems. Another way to look at it is more at a population level. We've got variation from person to person. We've got variation through the course of the day, dawn phenomena, different times when you're more or less sensitive to insulin. You have events that affect your physiology, the yelling at the kids or being yelled at by the parents or exercise. There's all these factors that change your insulin resistance as a function of events, and then there's things that change over time. So my son was 9 when he was diagnosed, now he's 20, he's gone through puberty. That's a very major change in both behavior and physiology. Pregnancy, exercise, all of these things mean that the same person can go through maybe 2 orders of magnitude difference in insulin sensitivity over the course of their life. That's a very challenging control problem. So this is a very important assertion. We assert that if you're going to build a scalable, commercial, safe and effective system for automation of insulin delivery, you really need to build a simulator first. One way of looking at this is like 1 hand clapping, 2 hands clapping. You really can't design and understand the behavior of a control algorithm in the absence of the system that you're trying to control. So the left side is a block diagram of a typical control system, and the right side is the plant or the system, the physiology that we're trying to control, and that's the simulator. So we transcended the challenge of experimenting with humans and replaced those humans with robots and are now using a simulator to characterize the anticipated performance. And you might be thinking, oh, that's scary, how could you possibly do that? This is a safety critical, life critical situation. Simulation won't work. Well, I would assert that although simulation may be new to the medical device development world, it's not new to other safety critical industries. So This is the first major place I worked. 30 years ago, we were using simulators for steady state process development. Subsequently, we were using it for model predictive control, using dynamic simulators, and ultimately using operator training simulators to develop operator competency. So in that example, we've been using simulation for a long time. My brother worked for Sikorsky, and he was developing simulators for competency development of pilots, again, in a heavily automated, very life-critical situation. Marius did a great job of introducing the concept of a model. I think of a simulation as being composed of a set of models, and those models are developed by data which contains variation. So simulation's got a bunch of models in it that are built from data. So you've got these 42 parameters that are contributing to blood glucose, 42 factors. Where do you start? How do you say we've got this world of variation in diabetes, and we need to build a simulator that will be useful for the development and characterization of an automated delivery system, automated insulin delivery system. So this is sort of our Pareto analysis of where are we going to go after first. And unsurprisingly, meals and insulin are the biggest factors. And what we found is that we still had to account for all these other things, illness, stress, exercise, medications, but do it in a slightly different way because we can't measure those inputs typically. So our simulator still characterizes those, we just had to approach it in a different way. I just want to talk a little bit about the data because that's the foundation upon which the simulations are built. And what we found very, very quickly is that diabetes data is not normal. And what I mean by normal is the traditional bell curve, the Gaussian distribution, and blood glucose is not normally distributed. If you remember one thing today, remember that blood glucose has a log normal distribution, a long tail distribution, and in fact, all of these other things, before I say that, it's frustrating to me or curious to me that the diabetes industry rediscovers this fact that it's log normally distributed about every 5 years. So I think next year we're due for another rediscovery of the fact that blood glucose is log normally distributed. In addition to that, all of these other things that we have found to be relevant and important to modeling of blood glucose also have a log normal distribution. So I would implore you, if you're ever tackling a model of diabetes, start with the assumption that your data is log normally distributed, and you'll save yourself a lot of time. At Bigfoot, models go through a life cycle on their way to providing some value. There's a famous quip that all models are wrong, some are useful. So in terms of the utility for which we build the models, we go through a governance process. So let's make a model, let's gestate that, let's go collect available information. Let's make sure that we codify that model in a very rigorous way through something like a single-page lesson or a data science report or an engineering notebook. And then we sort of release it into its intended use. So some of our models go into the simulator, some of our models are instantiated directly in the code of our pump in the firmware. And there's sort of three types of data that we consider in various levels, images, and quality. The first and the best kind of data is primary data, the data you collect yourself, the raw data that's coming out of a clinical trial or an engineering study. Secondary data is raw data collected by somebody else that's been posted on the internet or shared by a partner, but also is the raw data. That's a secondary quality. And then the tertiary quality stuff is the stuff you read in a journal article where somebody's already pre-masticated the data, chewed on it a bit, and summarized it in a statistical form. So you don't have the raw data. And sometimes we have no choice but to fall back to that. So we call our simulator at Bigfoot the V-Clinic. The V-Clinic was developed by another one of Night Scout's early contributors, Ross Naylor, who used to work with me at Medtronic, and I chartered him when he first joined Bigfoot to build a simulation factory, build the V-Clinic, and he has done a fantastic job with this system. I think it's one of the most valuable assets that we have at Bigfoot. This is the GitHub README page for the V-Clinic, just giving a little bit of an overview of what it does. predicts physiology, predicts behavior, or you can model those things, you can model events. And also we model the system things. You know, what's the transfer function for the continuous glucose monitor? What's the probability of an insulin delivery pathway fault? Because these are the things we need to know because they will happen in the real world. A couple more details. It's written in MATLAB, object-oriented, extremely fast. So it runs on a laptop. You can run it in parallel on a multi-core machine. And for our large sims, we just spin it up onto the cloud on AWS and can run very large simulations very quickly. And once the simulation results are done, we have a whole host of visualization and reporting tools that allow us to develop insights from those simulations that we just ran. This is, Brandon wanted me to have a little slide on this. Here's an example of one of the simulation runs. This is 60 days. That's scenario, where that says, scenario
029B.
29B. Okay, so we have a number of these scenarios where we know these are challenging situations in the world of diabetes, and rather than run a clinical trial and spend months to gather information on a particular scenario, this probably took 5 seconds for us to do.
This is inconsistent bolusing behavior.
Inconsistent bolusing behavior. There you go. This is the scenario. What happens if somebody does something different on the weekdays than the weekends? What is the expected result from our system? I don't want to leave you with the impression that simulation is a panacea. In fact, it is a complement to other methods of characterization, system characterization, that are well established, standard, mandated on the path to commercialization of a class 3 medical device. So those are all the things in blue, and unfortunately the slide doesn't show up, but there's a pink bubble around the stuff from user interactions all the way up to physiology changes, and that is the scope of the V-Clinic. One of the challenges is that when you're developing a system like this, it's a multi-scale problem. There's multiple time scales involved, from the megahertz level of Bluetooth radios to the years and decades of physiology and behavior change. And those are very difficult systems to characterize. Not only that, on the vertical axis, you're starting from nothing, where you don't even have a system yet, and ultimately you're going to be releasing and commercializing and post-marketing many systems across many different use conditions. So how do you evolve yourself up there and be able to characterize what's expected to happen? The good news is that these simulations that we built do predict outcomes. So we went through an earlier iteration of the V-Clinic 2.5 years ago on the path to our first CRC clinical research study trial, which so when we submitted our investigational device exemption to the FDA, we included a series of prediction runs from the V-Clinic using the exact protocol of the CRC study, and that's the lines in blue. And then once we completed the study, as you can see, there's very high concordance between what we predicted what was going to happen and then what ultimately happened. So simulation is actually hard, though. I don't want to leave you with the impression that this is easy and anybody can pick this up. It's taken us a tremendous investment in hiring just excellent people who have the deep experience to be able to build these models and not make some of the mistakes. Marius gave some examples of overfitting and over-parameterizing. There's many other pitfalls to simulation. One of the grand challenges right now with simulation is verification and validation. How do you know that you have developed a simulator that is accurate and has high fidelity in the domain that you're trying to represent? This is absolutely outstanding news for us, that the FDA is in fact a very strong supporter of modeling and simulation. This is a recent paper by Dr. Tina Morrison at the Office of Science and Engineering Labs, where she asserts, I think correctly, that the disadvantages of human experimentation are well complemented by the advantages of computer simulation. We can do these things very quickly, at low cost. We can explore use conditions that are wide and varied. We can control all of the inputs to what we're simulating. That way we don't have any risk of pollution of the results. There's some papers there from the FDA. Again, these will all be posted online. The FDA has cataloged a number of approaches to modeling and simulation, so they're not just looking at physiology simulation like I've been discussing today. They've been looking at all sorts of different ways to accelerate commercialization and approval of devices in a number of different disease spaces. And it so happens that we're leveraging or using a number of these approaches at Bigfoot. This is the most exciting thing I've seen from the FDA. This is a presentation recently given, used with permission from Dr. Morrison, where this is not my vision, this is the FDA's vision of the role that simulators will play in terms of evidence for approval of devices going forward. So you can see that they believe, as we believe, that there will be an increasing role placed on the use of simulations to present evidence and accelerate the approval of medical devices. And my belief is that over time, the role of a clinical trial will change from one of exploration to one of confirmation that the models are correct. What does this manifest for Bigfoot? Back when I was young, this is what things looked like that played music for you. It's called a stereo receiver, and it's got a bunch of buttons and knobs and dials and switches on it. And if you wanted to get good sound, you had to twiddle all of those knobs and buttons and dials. And they don't look like that anymore, right? They look like that. There's now a volume up and down button, and it just plays good enough music, and it's transcended the way that we listen to music. Data science and machine learning enable that transformation. And what I mean by that is it's almost like the audio engineers who developed that thing on the left didn't know how to make good sound, and they said, since we don't know what the right settings are, why don't we give it to the user to do that instead? It's they're even less capable of doing it. So what data science allows us to do in Monte Carlo simulation is sort of twiddle those knobs and get good enough sound across the use conditions and the population that we're trying to serve, so that we can sort of lock those buttons down and remove them from the face of the device, and thereby simplify the device. So Ben Kamens, who some of you may know, also in the diabetes community, amazing guy, he I think well characterizes the opportunity here. It is really easy to add a feature to a device. We'll just add another alarm. We'll just add another configurable parameter, right? Super easy to do that. It's quite hard to come up with a rationale for why you don't need a certain feature or function. And this is the red circle there, that data science and these models allow us to prevent the introduction of unnecessary variation and complexity in the design itself. Because once you put that into your system, you're never going to get it out again. Once you've got a settable parameter, you'll never be able to get it out. Your lead users will rebel. The FDA will say, well, you said that was necessary for safety, and now you want to take it out, but you just can't get it out. So this really helps us prevent complexity from entering into our designs. So I think this is the summary, the penultimate message I wanted to convey to you today is that as we're building this scalable system that we expect and hope to work across a wide range of users and use conditions, the only way we can imagine doing this is through the use of modeling and simulation. What we've been able to use it for is the actual original design of the algorithms. We've been able to use it to characterize the expected performance of the algorithms across a wide range of users and use conditions. We've even been able to use it to inform the clinical trial designs and the outcomes of those clinical trials. Because we can run these simulations for arbitrarily long periods, months or years, we can anticipate what the economic benefits are in terms of things like reduction of hospitalizations due to DKA or severe hypoglycemia, and then we can use those for engagements with investors or payers. So the simulator has allowed us to do a number of different things. And oh, by the way, You can do things to virtual humans that you would never be allowed to do to a real human. Well, let's deliberately introduce a fault. Let's put 2 faults in today. Let's give them a really weird situation. You don't need to go get permission from an IRB. You don't have any recruitment bias. The people who show up for clinical trials are a different cohort than the one we are trying to serve. So instead we can design and run our simulators, simulation population with the cohort that has the kind of engagement and behavioral factors that we think that we can best position to serve. And then the other little detail is it runs 4 million times faster than a human trial. So, and that confers some cost advantage, right? So we can simulate 1 person day for a penny versus if you were in one of these intensive clinical trials, that's about $1,500 per contact hour. So I just wanted to put a little plug in for We Are Not Waiting. We are not waiting to use simulators to hasten the development of our systems. There's the 20 assertions. I think I just about got them all in. And last and most importantly, we're hiring a Bigfoot. We believe Bigfoot is the most mission-driven team in diabetes, and we're the most data-driven. Thank you very much.